To the MicroCMA tutorial video. The first thing we're going to do is I'm going to show you what happens if you open the CMapp application software without turning the controller on. So I'll double click that, open that up. We get a message that says controller not found. So I say OK. This is the initial getting started optional dialog box that pops up. We can simply select this here and say don't show this again after it first turns on. But what it does is it stresses the importance of doing the initial outgassing and conditioning of the electron gun. So we'll turn this off. Okay, close this down. Now I have to exit the program again. So step one, I will turn on the MicroCMA controller, wait a couple seconds for Windows to find it, and then double-click again CMapp to open the program. This time we didn't get that message, so that means that the controller is talking to the software. Okay, so that's the initial turn on. Okay, now depending on which version of controller you have, you may have to set the emission offset. And so to do that, we open up the hardware properties dialog box and see the emission current offset here is set to 0 microamps. Okay, for this one, this controller, that's correct. So other controllers, that value might be 0.75 microamps or 0.65 initially. But here's what we want to do. So I've got this set to 0. I'll say OK. I open up the electron gun dialog box, turn my beam on to 2 kV, turn the filament on, and you see this microamps here and how that drops down? That's the leakage current on the high voltage module, and it takes a few seconds to stabilize. And so it looks like I have a little bit of an offset of 0.0015, 0.0014. So it's just slightly above 0. So what I could do in this case is I could shut this down, come back over here, and set my offset to 0.014. Okay, now let's turn on to 2 kV, filament on, watch this drops down, and now see that's closer to 0. So this gives us a more accurate emission current reading because the emission current is how many electrons are coming off of the filament. The target current that we measure with the picoammeter is how much current is actually making it down to the target. Okay, so this is basically called setting the emission offset value. Okay, so for this section of the video, we're going to determine the starting filament current. So I turn on the electron gun, I open the electron gun dialog box, and now I will go ahead and open up Actuel, which is our 9103 software, start sampling. Also notice over here, since I have minimized display, if I minimize the display here, it still displays the current, but it doesn't take up as much real estate. Okay, so first thing we have to do is we have to turn our beam on. 2 kV is a good starting point. Turn the filament on. Start ramping the filament current up. Now remember, you never want to go up past about 0.8 or 0.9 initially. So I can go up fairly quickly to 0.5 or 0.6, and then after that we want to go a little bit more slowly. So when I get up close here to 0.9 on this filament, we expect to see some target current. See, that's coming up. Okay, there's 0.9. So I have about 10 nanoamps of target current at this point. So the first thing we want to do is I want to adjust the wane out percentage here to optimize the target current. So I'll go ahead and lower this down and see if that raises it. Okay, that's the right way. So now I'll start dropping down the wane out while I monitor the target current. So now I'm getting up. So I'm just tapping this a little bit. I want to find at what point do I peak out on the current. See there, as I lower the wane out now, the current's actually dropping, so I will have to go a little bit higher. Okay, that's pretty good. Now I've got about 200 nanoamps of current. That's okay. I might drop it down a little bit. just a little bit under 200 nanoamps. So this is a good operating point for if we want to do the degas routine next. We're going to want to know what filament current we should turn this on to. Also, here's another little thing we'll set up right now as long as we're here. I'm going to go ahead and drop the filament current down a little bit to where we don't quite have any emission. So now I don't have any target current. See, that's dropped off to pretty much nothing. That's 0.747. So let's put the standby at, I'll say 0.75. Yeah, that's pretty good. Okay, so that's right on the edge of where it starts to emit. So now see if I take this back up to about 0.9 or so. Here's our current. If I go standby, current goes down. Also turn the beam voltage off. Go turn that off. Now it'll go from the standby back up to 0.9 amps, and the current should come up in a few seconds as well. Oh, I see. Let's drop this down. There we go. Now, as long as we're on this menu here, another thing we can do is once we find the optimum point for the wane out at 2 kV, so if I lower this down, see my target current is dropping. If I increase a little bit, target current's coming up a little bit till it peaks out right about there. Now I hit set point. It says set the 2 kV wane out to the value I have right now, and I'll say yes. So that means that at 2 kV, the wane out percentage will be 38.4, and that should be the correct value to give us the maximum current density. Okay, so what we've learned really is that we want to set this current to about 0.9. Let's use the fine here, get it up. I'll say 0.9. Okay, so let's remember that, 0.9. So we'll go ahead and turn off the beam, turn off the filament, close, and stop sampling. This section of the video, we're going to talk about the conditioning. So we'll go here under System, Conditioning, and these three dialog boxes, what they do is they deal with ramping the filament up, ramping the beam voltage up, and ramping the multiplier voltage up. And so remember that value that we set to, it's already set here at 0.9. We found that that turn-on value was 0.9 amps. That's about where we want to operate. And so here I can initially set the filament to turn on starting at 0 and going up to 0.9 amps over 20 minutes. Let's raise that up to, if this is your initial outcasting, you're going to want to go 30 to 60 minutes. Bring it up more slowly. Let's say 30 minutes, okay? That's fine. Now let's say, for example, if I wanted to change this value, let's say it wasn't 0.9. In order to change that, see it's still grayed out? I can't change that unless I first turn this filament off up here. Now I can change that. So let's say if this was down at 0.888 and I want to take it up to 0.9, bring it up to 0.9, say filament on. Okay, filament on here. Now the beam voltage is going to start at, you can start it at 0 if you want to, but 500 volts is really quite low. So I'll start at 500, and then we'll go all the way up to 3,000 volts. And then we're going to take this up, especially if it's an initial outgassing, after you've baked out and you've installed the thing for the first time. This is your first conditioning. You're going to want to give it some time. So I'd go a minimum of 120 minutes, but even 180 minutes. The longer you go, it gives it more time to condition the ceramics and the gun, and also for stuff to outgas. And then finally what it does, it'll ramp the multiplier voltage up starting at 0. We can go up to 1700 volts, and we'll take that up over a period of about 20 minutes or 30 minutes. 20 minutes should be fine. It does this without any beam voltage. So the filament is off and the beam is off, and it's just the multiplier, just outgasses the multiplier. And so I'll say start. And so now we have this bar here, bar graph, and it tells us, okay, this is the amps. See our amps are coming up very slowly. So and this is kind of like there's an algorithm here that the higher you go, the slower it goes. And so it's kind of like a rubber band. As you stretch it, it goes slower and slower and slower. So the initial outgassing, ramping the filament up, is fairly rapid, but after that it's going to start slowing down. So it'll take 30 minutes to go from here, 0.22, 0.25, in just a matter of a few, 15, 20 seconds to get up to all the way up to 0.9 amps will take 30 minutes. After that, the filament will stay on, so the gun is now warm, and then it's going to start at 500 volts and go up to 3,000 volts over a period of 120 minutes. And after that, this will turn off, the filament will turn off, and it'll ramp the multiplier up just by itself up to 1,600 just to give it a little bit of initial outgassing. Okay, so basically an hour and let's see, 2.5 hours, a little bit close to 3 hours later, this would be done. So you can set this up and just walk away and come back later. Okay, so that is the outgassing. Okay, in this section we're going to show you how to set the filament current limit. Initially I'll start sampling with my 9103 so I can see the current. Open the electron gun dialog box, come up to 2 kV, turn my filament on, bring up my filament current. That's the fine. Let's go to the course, step it up a little bit. Remember, we get up to about 0.8, we got to slow down. Okay, now as I go here, I'll start clicking one click at a time while I watch my current. Let me bring the current down so it's closer. And it doesn't take too long for this to stabilize. Probably about 5 minutes or so, and the gun is pretty stable. All right, so I want to shoot for about 300 nanoamps of current. So let's pop up our fine a little bit here. So 300 nanoamps, of course, is 0.3 microamps. Dropping it down a little bit. Okay, now let's fine-tune this wane-out voltage again. All right, that's pretty good. So this is 0.913. So what I can do is I can go to my hardware properties dialog box over here, 0.913. We want to set the filament current limit just a little bit higher than that. We don't want to go too much higher. So let me say initially I'm going to set it to 0.93 in this case. Okay, so that way if I accidentally run this thing up too high, I'm not paying attention and you get distracted, or sometimes the mouse just runs away from you, we're not going to go up way, way too high to where we're going to damage the filament. Let's run this up that high and see how much filament current it gets us. Oh, I have to say, okay, here, apply that first. This should stop at 0.93 now, and it does. And see, that gives us about a half a microamp, so that's not a whole lot of current, so that's relatively safe. If you wanted to go higher, get a microamp, you'd have to bump up the current limit a little bit, but we recommend most to operate the gun at about 300 nanoamps of target current. Gives you a good value of where you're not causing too much heat damage to your sample, or which can cause carbon desorption and adsorption effects, and also reduce the chance of arcing because you don't have a lot of outgassing happening in the electron gun region. But you can run it up to a microamp or even a couple of microamps if you want to. Okay, so there we go. So that's pretty stable. So that's basically setting the filament current. Now, as long as we're here, the other thing we're going to do is I'm going to show you how to optimize the wane out. We did it here. I'll hit that set point again. It says yes for 2 kV. Now, since this gun has already been conditioned, we can run it up pretty quickly to 3 kV. Okay. Now, see, the current is actually a little higher. Let's adjust our wane out here to maximize it. Oh, that's nanoamps. Okay, I got to come down. I was looking at picoamps and thinking it was nanoamps. Let's drop down. See, I'm bringing the wane out down. See, now we're up to about 250, 260, 270 nanoamps, 280. Now I'm going to just keep clicking this a little bit until it peaks out. It should peak out at fairly close to the 300 nanoamps that we had at 2 kV. Okay, there it is. Okay, see how I did that? So now I've got that optimized. I hit set point. It says change it to 3 kV set point to this value. Yes. Okay, now if I go to 2 kV, we should have about 300 nanoamps. And if I run up to 3 kV, all the way up, you see how that's staying nice and stable at 300 nanoamps? Oops, gotta hit it. There we go. So what we've done is we've just set the slope of the wane out voltage so that now no matter what voltage you select, we're always going to have maximum current density and smallest spot size to the sample. All right, that is called setting the wane out slope. Turn this off, stop this. the last thing related to the electron gun that we want to set up is the emission current shutdown value. And so just for demonstration purposes, I'm going to set this down low, like say 5 microamps, 5.0, and apply. Okay. Now we'll turn on our gun at 2 kV. Let's turn this off. Okay. Turn the gun on rather. Oh, I have to close out this box. Okay, 2 kV. Filament on. See, it starts out at about 2 microamps and drops down. Let's bring up our filament current. And again, turn on my 9103 so I can watch the current. I keep dragging it over here just for training purposes, but normally I like to keep it up in the corner. Remember that 0.9 or so, we should have about the 200, a little bit higher. Let it stabilize. Okay, so see, this is set to 1.5 microamps, right? So what I'm going to do now is I'm going to bump my filament current up a little bit. See how that's rising? Let's take it up to where it goes past 5. Oh, I can't. Duh, because of course my filament current is limited at 0.93, which was smart. So let's come over here, and now just for now I'm going to bump this up to 1 and apply. Now we can raise this up after I close this dialog box. Boom. See what happened? We went over 5. It said the emission reading was over the limit, so what it did is it shut down the beam voltage and current circuits. It shut it off, and we don't have any current over here. So that's another level of safety where what you can do is you can set the emission current limit so that, and see it automatically shut everything off. So let's go back to our dialog box here, and since that's really just an upper limit, okay, I'm going to set this back to the 0.93 that we had it set to. I'm going to put my emission current limit up pretty high, like 19. Okay. And apply. Okay. Come back, turn our beam on. Filament on. Measure the current. Target current, that is. Bring up the filament current. Okay, slow down a little bit here. And there we are, coming back up, and it'll stabilize in, fairly quickly to that 300 nanoamp value. Okay, so that is setting the emission current limit. Okay, so for this section, we're going to calibrate the elastic peak position and also the energy linearity. So I have a piece of copper loaded in. I've been running this gun, letting it warm up for a little bit, so now you can see up here I'm dropping it down to about 300 nanoamps of current. Okay, stop sampling. So this little alignment icon over here is for the elastic peak, or you can also go over here and go Acquisition. Technique is AES, of course. Oh, we'd have to go File, New to get that to open up. New alignment. Okay. Acquisition. New alignment. We can get to it here as well. All right. So that's one way to get to it. I like to also just hit this little icon up here, New alignment. So we hit the green Start, which will go ahead and set things up. It'll automatically ramp the multiplier voltage. And I've got the sample position about 3 or 4 millimeters away from the CMA and sample distance. So now I'm going to walk over here and adjust my Z translator. And you notice I'm not at 2 kV. At this point, I don't care where it's coming in at. I just want to try to find the maximum counts. So move it in a little bit more. See how the counts are coming up on the elastic peak? And now if I go through it, they'll start coming down. So I want to back it up a little bit. Find that maximum point. Okay, a little bit further in. Okay, that's pretty good. Okay, now I can adjust my focus as well. See if I defocus it a little bit. Beam gets broader, counts come down. Go back up to the focus, go through it the other way. Gets higher, fatter, starts coming down. So you want to basically have the sharpest elastic peak that you can get. And that usually focuses at about 11 o'clock or so on the focus knob. Okay, so this is the correct distance from the sample to the CMA nose because I'm getting the maximum counts. Okay, so I'll go ahead and stop this. So the reason we use copper is because it's got two convenient peaks for us. It's got a peak down around 60 EV differentiated and a peak at around 920 differentiated. So what I'm going to do is I'm going to just change the settings over here, value here on my alignment, and I'm going to go from 30 to 90 and acquire. And what we want to do is we should hopefully see a low energy copper peak down here. Okay, and that's a little bit high. See, we want this to actually come in, we want it to be 60 differentiated, and so that means that the peak itself should come in at about 58, something like that, 57 maybe. So on the front panel of the controller, I'm going to unlock the offset knob and I'm going to move that pod a little bit, and it's very sensitive. So what I'm going to try to do is find a spot. That's pretty good. Lock that down. Okay, when I locked it down, it moved a little bit. Let me go ahead and differentiate just to see where that peak is. That's pretty good, pretty close to 60. Okay, let's stop this. Okay. Okay, that's a pretty good initial value, but really what we want to do is we want to set this with the beam at 3 kV to get more of the higher energy. So I'm going to run this up to 3 kV, my beam voltage, and let's check that again. So hit the little green go button, hit the yellow button, then it'll save it. Oops, I didn't want to do that, I just wanted to stop it. Okay, smooth and differentiate. Okay, that's pretty good. Now let's go and we're going to change the parameters. So we want to look at the 920 peak differentiated. So for there I'll go from 900 to 940. All right, acquire. Now for this high peak, we're going to adjust the gain pot on the front panel of the MicroCMA controller. And for this I want it to come in about 916, 917, something like that. Okay, that's low. So I'm going to loosen that. And I'm going to turn this a little bit counterclockwise. All right, let's differentiate the data and see where that peak comes in at. That's pretty good. Okay, so I'll lock down the front panel pot. Okay, so now we've set those two peaks. We've got the low-end peak and the high-end peak set. We'll come back to our settings, and I'm going to go back to the 2 kV elastic peak settings and acquire the elastic peak again. Now, if the peak is not exactly at 2,000 volts, what we're going to do is we're going to adjust the beam voltage reference to set this to come in. Oh, this is a common mistake, so which I'm glad I did this. So let me stop this thing here. If I'm going to do the elastic peak, I've got to set the beam to 2 kV first. Okay, now reacquire. So if you see that slope during an elastic peak going up like that, that means your beam is at 3 kV. Okay, so you can see that peak's a little bit high, so I'm going to open our hardware properties dialog box over here, and we have the beam voltage scale factor, and I'm going to try, I'll just pick a direction. I'll just take it, hit 0 here, and apply that. So I'm going lower. Oh, that's the wrong way, so we have to go higher. So let's try 1.0. Apply that. Okay, see that brought it back in the right direction. We have to go just a little teeny tiny bit higher. So I'm going to go 1.01. Let's try that. Apply. Oh, 1.01 was way too much. So 1.001. Apply. Okay, that's pretty good. All right, so now we're going to go ahead and say OK to save that. Yes. All right, now what we should see is we can go ahead and stop the alignment. If I hit the red button, that means I don't want to save it. If you hit the yellow button, that means yes, I want to save the data. Let's do a survey. 0 to 1030. 30 to 1030 rather EV. You don't want to start at 0 because there's so much low energy down there, it's going to skew the scale. So never go really below 30 EV. You're not going to get any useful data by going below 30. And so we set the upper limit to 1030 just so that it's even increments. 10 sweeps, 25 milliseconds. This is pretty typical. Before I do this, as long as we have Actuel set up here, there's another feature we can set here. I'll go ahead and apply this. Is here it says use the 9103 to read target current. So I'll say OK, apply, OK, close that down. Let's sample for a second here, just make sure. Yeah, it's pretty good. It's pretty stable. Drop it down just a tad. Stop sampling. Okay, now when I do my survey, hit acquire the survey, what it's going to do is it will start out initially and watch what happens up here. It's going to go ahead and turn it on and off automatically. There. So the CMapp program went out and talked to the Actuel program and said, hey, what's my beam current? And so it recorded that. It won't display it here, but when it gets done with the end of the sweep, it's going to display the current. So that's a useful feature if you want to save the current when you're taking data. And that's, it's very important when you're comparing one sample to another to have the same current conditions. Let's go back to the hardware while this is running. And so current, scale factor, oh yeah, I was going to show you this. If you turn this off, if you're not measuring with the 9103, you can still manually type in the current that you took the data at. Okay, so now you see I'm taking this data with the beam at 2 kV. Normally, you don't want to take 2 kV. 2 kV would be useful if you're having a charging sample or something, but you always want to take survey data at 3 kV. So you see how big this peak is here, the upper end peak. As a general rule of thumb, you want to have your beam voltage be 3 times higher than the energy that you're scanning. And that's why with the MicroCMA, we have a 3 kV coaxial gun, so the typical range is 30 to 1030. You can scan up higher to higher peaks, but but realistically, if you get up to like 1500, those peaks aren't going to be as large. So what I'm going to do is stop this right here. Say stop, yes. I'm going to run my beam back up to 3 kV. Okay. Now let's go ahead and acquire. So at 3 kV, that upper energy peak is going to be much higher because my beam is now higher. It was only 2 times higher than the beam, than that peak when I had the beam voltage at 2 kV. With the beam voltage at 3 kV, that peak's going to come up. So this is the low energy peaks, some carbon. Now, one of the reasons we select 10 sweeps and 25 milliseconds per point is you can see that you have some noise here, and then for each sweep that you take, that noise is going to go down. So sweep 1, you can see the peaks there, but there's noise. And so by the time you get up to 10 sweeps, that's going to smooth the noise out quite a bit. The other thing that you notice is that there's a lot of dead space when you take a survey like this. So there are no peaks here, there are no peaks all the way up through here. These are all the same. These are all copper peaks. That's a copper peak, nothing up here. And so in that case, what you'd like to do is take a multiplex. Because with the multiplex, you can take a scan and you can look at just this high energy copper peak here and just the carbon, for example. And then you could, so you're not wasting time taking all this data where there's no data, all that acquisition time. The handbook data, of course, is usually taken over a survey. So if you're going to want to compare something, you'll do a survey. But to get quantitative data, you can do multiplexes. You get quantitative data with the survey as well. But the other advantage of a multiplex is if you have a small amount of something, a percent, 0.5% or something, you can resolve that if you take enough sweeps. And so what you can do with the multiplex is you can take, say, 1 or 2 sweeps on your largest peak here, and say if we were trying to pull the oxygen out here, I don't really see any. But if there was a small amount of something in there, like say this is also a copper peak over here, what we could do is take, if let's say hypothetically that was some other element, we could take up a scan, a multiplex scan on this peak, and because the copper peak is so big here, it's like 1.5 divisions, and this is much, much smaller, we could maybe take 2 or 3 sweeps of this peak, and then we could take like 30 or 40 sweeps or 50 sweeps of this peak. And what that'll do is that'll help to bring those peaks out of the noise. If you take enough scans, the noise averages out, and then you can resolve the peak. And then when you do the atomic concentration, the algorithm factors in the number of sweeps, so you get an accurate atomic concentration. Down here it tells us the sweeps, number 6 of 10. This is the taskbar, status bar. And and you can also see the previous sweep. This previous sweep is actually the total of all the previous sweeps. So the data gets added together with each sweep. That's why sweep per sweep per sweep, you start seeing that the noise goes down. So given enough sweeps, of course, you can have textbook data like the handbook, for example, the PHI handbook. A lot of that data was taken with a much, much higher current, like 50 microamps of target current. And also back then they used chart recorders and lock-in recorders, and so they could do a lot of tricks to average the noise out. And so that's why a lot of the handbook data looks just so perfect. But in reality, in the real world, this type of noise is pretty common. This is pretty typical. Even on newer, very much more expensive systems, you see the same amount of noise. Okay, sweep 8 of 10 coming up. I'll just let this run a little bit longer. I was going to stop the recording and then pick it up, but there's only 2 more sweeps left. So when this gets done, we're going to take a look at the, I'll show you how you can use the markers. So sweep 8 of 10. Sweep 9 of 10. 10 sweeps at 25 milliseconds takes a little bit over 4 minutes. If you were to go to, like, say, 20 sweeps or 25 sweeps, of course that's going to take longer, but then your noise is going to be reduced accordingly. So again, that's why I think multiplexes are so useful, because they allow you to focus the sweeps on the signal that you want to resolve, rather than spending all this time where there's absolutely no data. Copper is useful, and we use copper to calibrate the linearity, but because it's common in an inexpensive sample. But you can do it with anything as long as you have a high energy peak and a low energy peak. For example, you would not want to calibrate the span using this 60 peak of copper and the 274 peak of carbon, because the range isn't there. But if you have a peak of something, nickel or something, that has a peak out in this area, 700 or whatever, that's fine. Let me cancel out of here. All right, so now I'm going to smooth the data, differentiate the data, and let's show you what the marker does. Marker, if I slide out here, and what you're looking at is down here, at the bottom of the peak where that line intersects. Pulls up the element table, and what it's going to do is it's going to find the closest peak to where the marker is, in which this case copper is correct, and this should be carbon down here. Okay, and then now those are really the only 2 peaks. See, these are all copper peaks, and so now we can do an atomic concentration. Let me turn the marker off up here. This little thing here with the percentage is atomic concentration, and now we can see that the ratio of carbon to oxygen is about 30% carbon. So the sensitivity of carbon is much lower basically than, well, I guess it's much higher actually than copper. So here we go. That's our copper, and it shows that the peaks are in the correct position, and we calibrated the elastic peak alignment. So that's setting the elastic peak and also adjusting the linearity on the front panel. Once those are locked down, you don't have to touch it again. But it's very easy to change that. So anytime if you're not sure it's right, if you check something and you think one of your peaks is off a little bit, it's very easy to readjust that linearity offset and gain. Okay, in this segment we're going to move over to a different sample. So I'm physically moving my specimen stage over to another sample that I think is silver. So anytime you move your specimen stage or your sample position, you have to take another elastic peak. So I can reuse the same AES alignment, 1950 to 2050. That's our elastic peak. Our beam voltage is at 2 kV. So we'll go ahead and acquire. And I eyeballed it to where it looks like it's fairly close, but I might be off a little bit. So, all right. So now what I want to do then is, it looks like I need to move closer. Oh, wrong way. Right way. Here we go. Oh, that was the right way. Actually, have to move further back out. Okay, so I set that to 2000. All right, that is our elastic peak on silver. Let's see what that looks like. I'll do a sweep stop. You see where this is popping up, this thing that gives me a message that says save. You can set that up under the acquisition options. It says prompt to save after acquiring. That if you have that selected, every time you do a survey or any kind of data acquisition, it's going to say save. That reminds you so that you don't overwrite a file and you give it a name. You can also automatically export out to ASCII if you want to. Load previous settings for multiplexes and depth profiles. I would recommend that you have that loaded. Okay, so let's differentiate our elastic peak, smooth it. Okay, that looks pretty good. Let's do a survey. So again, we want to do surveys at 3 kV. So let's start sampling. I just came back from lunch, so I had to turn this back on, and looks like it's starting to stabilize. Okay, let's run our beam voltage up to 3 kV. Okay, stop sampling. Come over here to our survey icon, new survey, and we'll go ahead and acquire. I'll minimize the elastic peak and then go window, tau vertically. So here's our copper data. I'll now move the electron gun dialog box over there, and this is should be silver. Okay, that looks like silver. So we'll get a few sweeps of this, and we'll just see what this looks like. And then after this is complete, we are going to do a multiplex. You see where the maximum count up here is approximately 50, possibly 55,000, okay, 47 in this case. What it does is when it's the software sets the multiplier voltage automatically, what it will do is try to go to the upper end of the survey, because generally the background rises, and so the highest point of the survey is also going to be the highest point in terms of counts, and then it will set the multiplier voltage to be about 80% of full range, and that gives you a little bit of leeway. 80%, the maximum count is 65K, so therefore 47K is approximately 80% of 65K. All right, so we can see the sensitivity for silver is very good, and that's why a lot of data is referenced to silver as a sensitivity factor of 1, because it's got a fairly large peak. Okay, we're going to come back to this after the sweep is done. Okay, so we're back after having acquired that silver survey, and you can see here, I've already marked it, but it's silver. By the way, if you select the marker track here, it displays the EV and the counts down here, and then that vertical line, if you click on that, the element table pops up, and it will tell you that it thinks it's this because that's the closest peak from the element table. Okay. Element table is located under Edit Element Table, Auger. And here's where all the sensitivities are for 3 kV only, and for all the different elements and the defined windows for the multiplex, lower and upper limit, and the sensitivity factors that you can edit. If you want to edit that, you just click on one, edit, and you can change the range, the EV per step, number of sweeps, and all that. That's the default for the multiplex, and here's the sensitivity factor. Okay, and these are all fresh out of the PHI handbook. They're very similar to All the CMAs have basically the same sensitivity factors. They're pretty close. I'll say no, I'm not going to save that. Okay, so speaking of sensitivity, this is taken with about the same current, right? 296.7, 296.5, so very reproducible in terms of current. And you can see that silver, the signal to noise is better because of the sensitivity of the peak. It's got a higher peak. Differentiated, this is almost 4,000 counts here. Differentiated here, this is about 1,600 counts here on the highest peak right here. And so that's one of the reasons that the noise is higher depending on the sensitivity of the element. Okay, so what I've done here to demonstrate a multiplex is I've moved to just the sample mount, which is going to be dirty. And so now that I've moved the sample, first thing I have to do again is an elastic peak alignment. So I've already have one set up here. I highlight the box, make sure that I'm at 2 kV, and acquire. All right, it sets the multiplier voltage. Okay, I'm off a little bit, so I have to adjust my specimen stage. And once it's been calibrated, whether it's higher or lower counts, you don't really care. You're going to just set it up to cross over at 2,000. Because topography can give you some wacky effects. See, I just moved the sample just a little bit on the x-axis and the counts came up. Okay, so the elastic peak looks pretty good. We're centered. That's good. We'll stop the elastic peak. Now we want to do a survey. So I'm going to run my beam voltage up to 3 kV. I'm going to do a survey first just to show you. Let's get rid of this window here and do a new survey. And let's just do 5 sweeps so it's faster. Acquire. Window, tile horizontally. Okay, here's our survey. So the point I want to make here is that there's going to be a lot of dead space where there's no data, and I expect that if we're on the sample mount should be iron, so we expect to see some carbon, maybe nitrogen, oxygen, and also iron. Okay, so we can see that here we have carbon, and here's oxygen, and these are the iron peaks. So the point is that if we look at the noise level here, of course the noise is going to improve with each sweep. So first sweep it's fairly noisy, second sweep the noise will start coming down as it averages out. But you see the height of these peaks out here, these iron peaks, relative to the carbon, they're much smaller. And it looks like we do have nitrogen right here. While that's acquiring, I'll show you another little trick. My preference for the marker is to, like I have it here, where it just marks and then when you click, then the box will pop up. You can do it another way here, where you can go Data, Options, Display Marker while tracking. If you turn that on, now when you mark, you move the cursor, you see over on the left-hand side here, all the elements will pop up. And so if I want to go up to this peak and say, okay, I think that that's iron, see they're right next to each other, 650, 651. I know that's iron. This should be iron here. Yeah, it is. See, and this is another iron peak down here. There it is. So we can just confirm that that's iron. You can set this up and leave it if you want it to be that way. My preference, though, personally, is I don't like that. I just find it too distracting, so I turn that off. All right, so we got one more sweep to go. Well, actually, we can stop this sweep. I just want to make the point that if we just want to look at carbon, oxygen, and iron, we don't want to be wasting time here and here and here. And actually, that could be nitrogen. Let's see what that is. We'll go back and do it again. Data, Options. I'll turn that on. Oh, silver. I don't think so, but that's nitrogen. Okay, so here's what we're going to do. We're going to set up a multiplex. So we're going to we can do acquisition, new multiplex, or you can also hit this little icon up here, which is new multiplex. Okay, we want, this is, by the way, this is loading the previous multiplex that we did. So I'm going to remove that. I want to add carbon, oxygen. I want to add nitrogen, I think I said. Oh, by the way, I can just type N, will jump us right down to the nitrogen. Okay, add that. And okay, I'll remove that. I didn't want that element. And then, of course, iron. Type Fe. Sorry, add. Type Fe. And I think Fe2 is the larger peak, so we'll take that one. Okay, so now what we have here is it tells us how many sweeps we have, how many cycles rather, and how many sweeps over here, and the EV per step and the range over the peak. So the largest peak is carbon, so let's look at that. Carbon's got 10 sweeps. No, we don't need 10 sweeps. Let's take 2 sweeps on carbon. Okay, oxygen is almost as big as carbon, so let's take 3 sweeps on that. Nitrogen is really small. This is it here. It's pretty small. Relative to that, it's a small fraction. And so if I went 2 sweeps there, I think I'm going to want to go 30 sweeps at least on nitrogen. And then on iron, relative to carbon, it's about 1/4. So if I went 2, that would be 8. Yeah, let's go 10 sweeps. All right. Number of cycles, 2. So this total time is only going to be about 3.9 minutes. So let me do this. That's not bad, just for training purposes. But let me say I'm going to go ahead and set this to 4, because I'm going to stop the video, and then we're going to come back to it. Okay, I'll say acquire. Apply, then acquire. As soon as it starts acquiring, up here we can see it's measuring the current for us again. Okay, once that hourglass goes away, there, okay, it automatically opened each window. So this is the first region here. This is carbon. Here's oxygen. Nitrogen. So see, we can see a little peak here, but as more sweeps go through, that noise is going to go down, 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 and that peak's going to become resolved. Okay, I'm going to pause the video here, and then we're going to come back at the end of this multiplex. Our multiplex has completed its acquisition, and what we're going to look at is some data massage options that we can do here. So I'll get the electron gun all the way down. Remember, this was the original survey that we took, and we can see here with just 5 sweeps that, yeah, we've got carbon. This is, by the way, is a low energy iron peak. And carbon, oxygen, iron peaks, you know, somewhat noisy. So what we did then is we took a multiplex where we're scanning just these peaks, just these regions here. And let me move this down, move this one down, go window, tile horizontally. Okay, so now we can see the nitrogen, which was barely even visible after taking a lot of sweeps on it, 120 sweeps. We can see we have a peak. It's pretty good. Now, if I differentiate it, and then smooth, you know, there's still some noise in there, even at that level. So one way you can get around that is let's revert. You can go into data options, and the default for smooth is 5. And if I increase that value up to, say, 13, so it's going to take an average over 13 points now instead of 5. Now I can smooth it, then differentiate it, and then there's the smooth, and then see, so it's not nearly as noisy. So the other thing you can do with multiplexes now is you can determine the area of interest for the peaks, and to do that you select endpoints. So now if I click from here over to here and let go, it's going to take, this is the maximum value and this is the minimum value to get the peak to peak that it's going to use for the atomic concentration. I can do the same thing on this peak, same thing on this peak, and same thing on this peak. All right, now let's blow up the other window here. And now that I've selected the endpoints and the data is differentiated, I can do an atomic concentration. And what this gives us now is the percentage of those peaks. So one new feature that we have is that we're going to be, instead of having this bar graph, it's going to display the actual data sets, like here, the actual differentiated peaks, in order starting at low EV to high EV. So it's going to look like a survey, but it's not going to have all the dead space in between. And then this is going to be in a table form at the end. On the last column, it'll say, you know, the percentage, similar to what it does for surveys, atomic concentration in a survey. So that's a new feature that's in the works and should be coming out fairly soon. But in the meantime, this at least can tell you that, yes, I've got 54.9% carbon and 27% oxygen and 4% nitrogen and 14% iron. And you could also then, you can go edit, copy as ASCII text, and then you can paste that into Excel if you want to get access to the raw data. So the advantage of a multiplex then is that you don't have to spend a lot of time to get that nitrogen to pull out here, as well as what we saw with the multiplex. We'd have to take essentially, you know, 40 or 50 sweeps. And so instead of doing the entire survey 40 or 50 times, we're acquiring just the areas of interest. Okay, that is multiplex. Okay, this is going to be an overview of the software, all the software commands in CMapp. We have file new, would be a new survey, a new multiplex, or a new alignment. Depth profile is coming, it's not quite there. Alignment is elastic peak generally. Survey is a wide scan, multiplex is a series of narrow scans. Open would be opening a previous file. And of course close, these are all standard Windows commands. Save, save as, send email. Importing would be from importing actually from our other program, Auger Scan. Export as text allows you to export the data set as ASCII, and export all would be selecting multiple files to export at the same time. Print, print preview, print setup, page setup, these are all standard Windows features. Edit copy, copies it to the clipboard, the data set to the clipboard. I mean, rather the image. Copy as ASCII copies the ASCII underlying, you know, the raw data set to the clipboard, so you could paste it directly into Excel. Markers and those are grayed out right now, so let's go back to Window, tile horizontally. Let's pick something here, like a survey, for example. See, now mark and track are available. So if I click mark track, as I move my cursor left and right down here, it indicates the EV and the count. Over on this side, it's showing us the marker, showing us which peaks it thinks it is. Markers, we've got just one marker picked right here, for example, silver. If we want to add another marker, I'll pick something over here, like sometimes there's a very small amount of sulfur. Don't really see it, but I'll pick it here anyway. Okay. So now I have two markers, edit, markers. If these are highlighted like that, if I wanted to remove it, I would click remove. If it's checked, that means it's going to be included in the atomic concentration table. Okay, so if I have these two parts fixed, these two elements, silver and sulfur, I can now do an atomic concentration, and it gives us the percentage of the elements based on height, peak to peak height, times the sensitivity factors. Endpoints and select endpoints, that's used for multiplexes. So let's look at a multiplex here. Window, display all regions. So here we can go edit, select endpoints. See, if I move my cursor left to right, if I pick a point and then click on the left mouse and then drag over to the right side and then release, that'll set the window. Whatever's within these two bars here, those are the peak that would be used in the atomic concentration calculation. So for example, over here, let's look at nitrogen. I have, you know, this is the peak selected here, and it's fairly small at 4.1%. Well, let's say if I'll pick a marker instead, I'll pick this other peak over here, which we know is not right, but it's much smaller. See, now that went down to 0.7%. So back over here, this is the real peak that I want to use. Okay. So that's endpoints. Annotation is if you want to write something on your survey. This is my data. Okay, then I can click and drag it wherever I want to. If I double click it, I can change the font, the size, the color, the style. Okay, you click it again, you can drag it wherever you want to go. You want to get rid of it, highlight it, just hit delete. Element table, Auger. We only have one voltage, that's 3 kV. And this is the where the lower limit, upper limit, and sensitivity factor is stored for the calculation for the atomic concentration. So these are textbook values that are right out of the PHI handbook, and you can use these. They're going to be fairly accurate. You can dial them in a little bit if you have a standard, and also if you want to create a new, like you have some kind of a film that you made or something, you want to add another type of element combination, you can add those here and then give it a sensitivity factor as well. So we'll click something like, here's fluorine, for example, edit. This is the range, lower limit, upper. This is the peak differentiated peak, the range, EV per step, default number of sweeps for a multiplex, and then the sensitivity factor. I'll say no to the changes. Toolbar. Main, acquisition, and region selection. These are these regions that are all here. These are the toolbars here. Region selection is not shown. Let's go ahead and check that. Now that's interesting. Let me see if that works with a multiplex. View. Nope, that's not available yet for this version. That'll be coming later. It's not really necessary anyway. Zoom. Click on Zoom, and it allows you to view zoom. Notice the cursor changes to a magnifying glass. Now if I click and drag my left mouse button, when I release it, it zooms in. View, restore, puts it back out. Raw data or transform data. The data is double buffered. So the raw data is here, and the transform data or massage data is here. Cycle times, depth, this is all going to be added in for the depth profiles. View options, this is where you can change things like the fonts, the graph, the line style, annotations. General is you want to have the survey regions in their own windows when acquiring data. You want that to be checked. And display previously collected data during survey acquisitions, you want that to be checked as well. That's where you can see the data as gray. While you're acquiring in real time, the previous sweep will show up as gray, so you can see that it's stable. And you can also see the signal to noise improve with each sweep. Okay, start, acquisition start, that's the same thing as hitting this little green button over here. Stop is the yellow button. If we were actually acquiring something, that would show up as yellow. Stop now is red. That means I don't want to save the data. Continue, you can add some sweeps, for example. If I took some data and I said, geez, I think I want to give it another 10 sweeps just to improve the signal to noise a little bit, you could add that. Settings, survey settings. These are the settings that we took this survey at. 30, 1030 for the upper EV, 1 EV per step, 10 sweeps to 25 milliseconds. Edit gun settings. This menu is going to change, but basically what it shows us is that we took it at 3,000 volts. And then for the sputter rate calculation for the depth profile, this is where you'll load that information and what your sputter rate is. A lot of this stuff is for a different electron gun that we've just pulled out of our Auger scan software, and so this is going to get changed and to match the CMapp. So some of the stuff that doesn't apply is going to go away. Edit. Edit is you can shift the survey a little bit, and you can also reduce it. Like let's say here I don't want to go above, I'll say 430. Okay, that zooms in like that. Now the thing about edit, you have to be a little bit careful. See, the data is double buffered, so I can't lose it. But if I'll say revert and go back to raw, see that data, that 430 now, that's my new limit, so that's gone. But don't panic. So what you could do is I could say, okay, I meant to do this, and I would just simply say File, Save As, and I'll save this as another file name. Or this is what I want to do rather, and I'll just say Save. Or I'll say Save As and save it as another file, in which case my original file is still intact. Or I'll just simply close it, and I won't save the changes. Now if I go back and open it again, it's right back where it was. So edit, you just need to be a little bit careful of, because that's one thing that you could, in fact, you could lose some data if you're not careful. Sample properties, this is really a holdover from another, from a multiple specimen stage, but you could put a comment in here that would show up in the printing. New survey, new multiplex, new alignment. Okay, that's another way that you can go File New or Acquisition New. Options, prompt to save after acquiring. If you turn that on, I recommend that. Then every time you get done taking a data set, it'll say, it'll ask for a file name. So that helps you to not overwrite existing data files. Load previous settings for multiplexes and depth profiles. Yes, we want to do that. You could automatically export as ASCII if you wanted to do that. And all these other things in here. But mostly it's just this prompt to save and load previous settings. Okay, data, revert to raw. Edit raw data as a text editor, so if you have like a noise spike or something, you can go in there and modify it and to clean it up. Differentiate smooth. See, differentiate is grayed out because it's already differentiated. So we'll revert back to raw. Now data, differentiate. Data, smooth. Shift, if you had a little charging, not usually with Auger you don't have that kind of charging, because if it charges, it's charging so severely it's very difficult to even take the data, and you have to do some things like reduce the current, change the angle, reduce the beam voltage. I mean, some samples that are pure insulators are very difficult to get Auger data on. Works best with semiconductors and metals. So you're generally not going to have much of a charge with Auger, but if you did, you could click on the shift here and you could shift it up an EV or two to bring it back. Atomic concentration. So once we selected the peak of interest or peaks of interest, it'll take the height of the peak times the sensitivity factor. So in this case, it's 100% because I only have one peak selected. This is the font that we had selected previously, so I'll click on this, go back to font. Now let's change that color back to black. Data options, differentiate number of points 5 and smooth. These are typical values. You could increase this to perhaps 7, for example, and it works like a combination of smooth and differentiate. Let's try that. See? System, electron gun control. This is where you will access the electron gun parameters, the beam voltage, the filament current, and the wane out voltage. Conditioning. This is where we outgas the filament, run the beam up, condition the ceramics and all the lenses to give them a chance to outgas and bring the high voltage up slowly, and then also initial outgassing of the electron multiplier. Sputter is a time sputter. If you click this, if you have an ion gun on the system that's tied into the focal point, you could say, okay, give me 5-minute sputter, start, and then you should see the sputter light. No, there is no sputter light on the controller. But what happens is on the back of the controller, there's a TTL BNC, and that you can cause that to go either high or low when the ion gun is on. Okay, so for most applications, though, we're finding that people don't even have ion guns on the systems. If they do, for a lot of people are just growing films in vacuum and looking at them immediately, or they're heating the samples up and then looking at them immediately. Ion gun control, that should be grayed out. Hardware properties. Okay, this is where we set things like the filament current limit, scale factor is always 1, emission shutdown, emission current offset, beam voltage scale factor, energy scale factor should always be 1 because we adjust the linearity on the front panel pots. You can use the 9103 picoammeter to read target current or not. If you don't have that selected, then there's a little box in the survey window when you set up a survey, and you can just type in what the current is there. And let me show you how that works. Let's apply this here and close. If I do a new survey, see this box down here, target current. So you could just manually type in, 300 nanoamps, for example, and I can apply that. So if you have a Keithley, you can take that measurement. If you have the 9103, it's going to work automatically. And for some systems, they don't have a picoammeter because you have no way to measure current because your target is grounded all the time. Multiplier properties, this is where we select, these are the defaults here for how far up the multiplier gets ramped. For alignment, it's 30. It's percent of maximum counts, 30%, 80%, 50, and 50 for profiles and multiplexes. Actually, multiplexes, I think it makes sense. We'll bump that up a little bit higher as well. I'll go up to 80. What's supposed to happen is it's supposed to select that on the highest kinetic energy, so that will reduce the chance of saturation. Default voltage, this is as high as the voltage will go up to, is 1400. If I turn the auto EMS off, it's going to set the voltage to 1400. So that's useful if you're conditioning or troubleshooting, but in general you're going to want to have the auto EMS selected. If you want to acquire a gain curve, you just see what the multiplier looks like. You set the multiplier voltage, you'd set the beam current down to where you only have about 10 or 20 nanoamps of current, and then you would run the gain curve and you'll see a display of counts versus voltage. And you want to, it just tells you the condition of the multiplier, but basically you don't want to go much higher. Once it plateaus out and you get a flat line on the top, you'll pick about 100 volts past that, and that's where you want to set this value. There's no sense running the multiplier up any higher than where you stop getting counts for an increase in voltage. Gun properties, same thing. A lot of this stuff doesn't apply. It's mostly just the beam voltage. Beam voltage that was set up. In this case, this is the last beam voltage that the electron gun control was set to, and the beam current. And so the emission current didn't show up on here. Emission percentage. So a lot of this entire dialog box is going to be changed in the near future. In this segment, we're going to talk about how do you determine the correct operating point for the electron gun if you can't measure the target current because your specimen stage is always grounded. The way you do that is you're going to set the multiplier voltage first of all. This auto EMS, we're going to turn that off, and we're going to set the value down to about 1100 volts. 1100 volts is typically the correct voltage for an elastic peak. Okay, so now we want to go to our electron gun menu, turn it on, the beam voltage, turn on the filament current, slowly bring up our filament current. Remember, you get up to about 0.8 or so, you've got to slow down. Now, remember that there's a ratio, and typically it's about 10 to 1. It can vary. Depends on the sample and how far away the electron gun is and things like that, but approximately 10 to 1. So that means if I've got 1.3, 1.4 microamps, I probably have about 140, 150 nanoamps of target current. So what we're going to do is we're going to set up an elastic peak, which is 1950 to 2050. My beam voltage is at 2 kV. I'm going to acquire. Okay, that was a pretty good guess because you see we've got about 37,000 counts. We don't want to go up over about 60,000. If you go up too high, you're going to have a straight line. It's going to saturate. And I'll show you what that looks like. We'll come in here to actually I'm going to increase my filament current a little bit, which will give us some more target current. There. Remember, I set my limit previously to 0.93 amps, but you see this flat line on the top here? That corresponds to 65,000 counts. That means the multiplier is saturated. Counts can't go any higher than 65,000. So what I want to do is I want to drop my filament current down to where I'm not saturating. Okay, so there we are. So The other thing I can do then is I can try adjusting the weight out voltage. I can optimize my weight out voltage by looking at the elastic peak. So I'll increase it. See, now my counts are coming down. So I'll drop it back down. Counts are coming up. Counts are coming up. Now it's pretty level. But keep dropping the weight out. Counts come down. So I'll go back up a little bit on my weight out. Okay, so for an elastic peak, about 1100 is correct, and that gives me about 2.2 microamps, so that means I'm probably about 220, 250 nanoamps of current. 2.2 microamps equals 220 nanoamps approximately. But that's good. I'm not saturating. I could move my sample in and out to set the elastic peak and to get my data. Now for a survey, you're going to want to do the same setup, but what you're going to want to do is you're going to want to bump up the multiplier voltage. Actually, that's not true. Now that I've set that, and we think that that's about the right setting, I can go back here and turn the auto EMS back on, and I'll set my upper limit to 1400 volts. Okay. Now we're going to assume that we have approximately 200 or so nanoamps, and I'm going to go ahead and do a new survey and acquire. And let's see what it sets the multiplier voltage to. Typically, you're going to be somewhere around 1200, maybe up to 1300 volts for a survey with 300 nanoamps. Okay, so we're pretty close to 1200, 1190. So that tells us that this voltage is probably correct, and that our current is probably in the range of approximately 300 nanoamps or so, which is what we want. So you're not going to get the same level of reproducibility without being able to measure the target current that if you have a picoammeter. However, this is still a pretty good representation. So if you know, okay, about 2.2 microamps, maybe I could go up to 2.5 microamps, for example. But that's what you can use. So you're going to use this emission current to give you an indirect measurement of the beam current. And you just want to make sure that you don't increase the beam current too much to where you have issues like saturation of the multiplier or just too much emission. You want to keep your emission, below 3 or 4 microamps. All right, so we could take additional sweeps on this, but I'm just going to go ahead and stop that. All right, so to review then, let's see what happens here if I bump up my current a little bit. About 2.5 microamps. Remember that last survey was about 1090 on the multiplier voltage. Let's acquire it now and see what happens. If I've increased my emission current, that should have also increased my target current, and so now the multiplier voltage should have to be a little bit lower. See, a little bit lower, 1175. So on the other hand is if I have let's stop this. On the other hand is if I have less current, way less current, okay, now let's acquire. Now it's going to ramp the multiplier voltage up higher. And if you get up to where you're at 1400 volts and you don't have adequate signal, then that means that you need to increase your target current or your emission current. Okay, this is still not too bad. It's 1240 volts. So we probably have approximately 120 or so nanoamps of current. Let's drop that down further. Oops. Up here. Filament current. Okay, there we probably have about 50 nanoamps. Now I'd expect that the voltage is going to come up higher. Might be 1300, closer to 1400. Nope, still 1275. It's coming up, but so But that's the general idea, is that the higher the voltage, that means you don't have enough current, so you'll still get data, but it's going to take more sweeps because the signal to noise is not going to be as good as it would be if you had a higher current like 300 nanoamps. 300 nanoamps compared to 50 is quite a bit more, of course, but still 300 nanoamps is not that much target current. Okay, so that's pretty much how that works. Go ahead and stop this acquisition, yes. And that is how you determine the correct operating point without having a picoammeter.